To the pilot in flight, to the air traffic controller on the ground, and to the meteorological officer making weather forecasts, radar gives new and extended vision. To all who fly, radar means added safety. Let us see in a general way how it works and where it is used in civil aviation. A radar system has 5 main parts: a radio transmitter, an antenna system, a receiver, a control system, and a display unit with a viewing screen. The transmitter generates radio frequency energy in short bursts or pulses. These radio pulses go to an antenna system, which sends them out into space in a highly concentrated, narrow beam. If some of the pulses strike an object, they rebound, and some of their reflected radio frequency energy is returned to the antenna system. The reflected energy in the form of weaker pulses is carried from the antenna into the sensitive radio receiver, where the pulses are amplified and passed into a cathode ray tube, in which the radio energy bombards a fluorescent coating inside the tube, or scope as it is called, and leaves a visual glowing area of the object struck by the transmitted pulses. The whole process of generating pulses, transmitting them from the antenna, receiving the echo from an object, and producing an echo on the scope takes only a minute fraction of a second. For example, it will take about 100 millionth of a second for a pulse to travel out to and return from an object roughly 10 miles away. Depending on the use to which radar is being put, pulses are generated at rates of something less than 100 per second to up to several thousand per second to provide a continuous picture of radar echoes on the scope. The beam of radio energy put out by the radar antenna is narrow and highly concentrated and can be rotated or directed as needed. For example, a vertical beam can be rotated through 360 degrees of azimuth, or it can be moved from side to side. A horizontal beam can be moved up and down to provide return indications about the height of objects. The beam's pulses travel in straight lines and can be reflected only by those objects immediately in their path. The pulses are returned by the nearest reflecting objects with which they come in contact. They will not bend around one reflecting object to detect another, or go through one reflecting object to detect another. This characteristic of the radar beam makes it difficult to detect ground objects beyond the Earth's horizon. To make antennas detect objects in different areas, they are mounted in a variety of ways. Any radar scope is designed to give a picture of the area scanned or covered by the particular antenna associated with it. And the movement of the antenna can be followed by watching the trace line on the scope. The direction in which the antenna is pointing at the instant it receives a return pulse from an object determines the position of the echo on the scope with relation to the point representing the antenna location. Knowing this, an observer can tell the direction of an object by the direction of its echo from any known location on his scope. The center of this scope represents the location of the antenna. If an object is far away, its echo will appear near the edge of the scope. If an object is closer, Its echo will be nearer the center of the scope. Range marks on the face of the scope enable an observer to determine the distance of an object. A radar picture of an area with an aerodrome at its center may include echoes from surrounding hills, aircraft, and some types of clouds. Depending on what use an observer wishes to make of the picture on the scope, he can adjust controls to regulate the relative brightness of different kinds of echoes. The unwanted echoes are known as clutter. The basic principles underlying the operation of all types of radar are very much the same, and they can be adapted to many uses. Surveillance radar equipment used at busy aerodromes and along some air routes help air traffic controllers to detect, identify, and direct the movements of aircraft traffic. Controllers see aircraft in the 360-degree area covered by SRE scopes as moving spots of light, each representing an aircraft to be controlled. Radio telephone is used to give pilots control instructions and headings to fly, which guide their aircraft into and out of aerodromes and along air routes safely with a minimum of delay. An air traffic control radar beacon system, properly known as secondary radar, extends the normal range of radar and reinforces primary radar echoes or spots of light which represent aircraft on the SRE scope. A very simple explanation of how it works is all that can be given in this film. A second antenna is aligned with the primary radar antenna. The beam from this antenna striking an aircraft equipped with a transponder causes this special receiving and transmitting unit to send out a return signal automatically from the transponder antenna on the underside of the aircraft. The transponder signal received back at the secondary radar antenna is much stronger than the reflected radio energy signal being received by the primary radar antenna. This stronger signal is also seen on the SRE scope, aligned right with the primary echo. It is a much stronger, brighter spot of light. In addition to extending and reinforcing the primary radar, the secondary radar can be made to furnish identification and altitude information through the transmission of coded signals. Precision radar is used in conjunction with surveillance radar to determine more precisely the exact altitude and distance of aircraft within 10 miles of the aerodrome. It provides the controller with a two-part picture. An elevation antenna sends out a beam which sweeps up and down through an arc of 7 degrees to provide the precision controller with the display of the height of aircraft with relation to the correct glide path to the runway. An azimuth antenna sweeps from side to side through an arc of 20 degrees and shows the precision controller when an aircraft is to the right or left of the center line of the runway. When cloud ceilings are low and visibility is greatly reduced, ground-controlled approaches, GCA, may be made with precision radar equipment. At some aerodromes where fog is a frequent hazard, ground controllers use radar to watch and direct taxiing aircraft on the aerodrome. In this scope, outlines of the runways and taxiways show on the face of the scope, and aircraft are clearly seen as they are directed carefully to and from the runways. With radar, a steadier flow of controlled air traffic can be maintained into and out of aerodromes and along air routes, day or night, in good or bad weather. Meteorologists use radar to detect weather disturbances and to observe their direction and speed of movement as an aid to weather forecasting and flight planning. For weather radar, an antenna is mounted well above the ground level to minimize interference from nearby buildings and surrounding terrain. The antenna rotation, or angle of elevation, can be altered at will by the observer at the scope, so that the radar beam scans distant and close-range storm areas more effectively. Different antenna settings enable an observer at the weather radar scope to determine the height, distance, and intensity of storms scanned in the area covered by the antenna. A scope with the antenna trace line centered will give a 360-degree picture of the surrounding area. And depending on the range setting selected, the distance covered may be as little as 5 miles to as much as 250 miles. The center of the radar picture can be offset in any direction and the range setting adjusted to enlarge a section of the area for a more detailed study of the weather. Tilting the antenna up a little each time it revolves gives the trained observer a cross-section of the height of weather seen on the scope. Tracings, radar graphs, photographs, and time study motion pictures can all be made of storm movements through areas covered by weather radar. Trained observers can determine a storm's growth and decay, direction and speed of movement, intensity, shape, and other characteristics. In addition to radar being used on the ground to provide pilots with air traffic control instructions and weather data, more and more civil aircraft are now being equipped with airborne radar, used primarily to detect and avoid bad weather. This equipment is a lightweight, miniaturized version of ground search radar and operates in much the same way. It has a transmitter, a receiver unit, a small scope or indicator, a control panel, and an antenna. The antenna is mounted on the nose of the aircraft behind a plastic dome. It rotates through 360 degrees of azimuth at a rate of 15 revolutions per minute. During part of the rotation, the scanning beam is interrupted by the aircraft itself. Nevertheless, the antenna provides a useful azimuth scan of more than 180 degrees, which covers the flight path of the aircraft and at least 90 degrees on either side of the flight path. The antenna is usually stabilized automatically by means of a gyroscopic control unit which compensates for the normal pitch and roll of the aircraft. The airborne radar indicator is generally a 5-inch PPI scope mounted in or near the center of the instrument panel. Other locations and additional scopes may also be used, depending on the type of aircraft and the pilot requirements. Pilots experienced in the interpretation and use of radar indications can detect bad weather ahead and locate areas of heavy precipitation and severe turbulence. Usually, pilots are able to find a safer, smoother corridor through the storm. If not, a change in flight plan would permit a search for an alternate route through, around, or over the bad weather. The applications of radar to civil aviation requirements are many, but wherever it is used, the basic thing it does remains the same. It probes the skies beyond the power of human eyes to help watch safely over aircraft and all who fly in them.